Hello and welcome. I'm Steven, and this is my inorganic presentations on market theory and the algebraic mechanisms of redox reactions between two metal complexes. The study and manipulations of valence electrons could be one of the definitions of chemistry nowadays, and the transfer of electrons between the molecular compounds is therefore an extremely important phenomenon. In these presentations, I will consider the electron transfer between the two inorganic complexes, and there are definitely two mechanisms I want to talk about in which the inorganic complexes can transfer electrons. One is the algebraic mechanism, and the other one is the inner sphere mechanism. The algebraic mechanisms are electron transfers occurs between the complexes that do not undergo substitution, in which no new bonds are broken or formed. And the inner sphere mechanisms are electron transfer occurs between the complexes through a bridging ligand, and at least one of the complexes needs to be liable to allow the bridge to form. The bonds are broken and formed. And in these presentations, I will be mainly focusing on the outer sphere mechanisms instead of the inner sphere mechanisms. If you have a closer look on the long definitions on the right hand side, we can draw conclusions that metal centers do not form a bridging ligand in these mechanisms. The reason this phenomenon may occur is because both the reactants are inert and the redox sites constrained to be far apart. And before we move on to the market theory or market model, I want to first introduce you the overall outer sphere electron transfer mechanisms and their steps. And here is the overall mechanisms reaction of outer sphere electron transfer, in which the oxidant is reduced and reactant and reductant is oxidized. Apologies. And I can break down the mechanisms into three small steps. The first step is the formation of precursor complex. And the second step is the activation of precursor complex, electron transfer, and reduction of successor complexes. And the third step, and last step, is the dissociation of successor complex, in which we can get the final product of this. The formation of precursor complex and dissociation of successor complex are very fast, but the electron transfer is extremely slow. And if we see this as a graph, we use the G Gibbs energy against the reaction coordinate. We may get a graph like this. So we see the x-axis will be the reaction coordinate, and the y-axis would be G as Gibbs energy, and we may get a graph look like this. in which we can get reactants to begin with and product as at the end. The first peak would be our precursor complexes, and the second one would be our successor complexes, which is slightly lower than the precursor complex. Our delta G would be the gap in between the reactant and product. That's delta G, changing energy, and our delta G double Jagger would be from here to the top peak. Now I think it's the perfect timing to introduce the market theory properly. We first need to understand a term called the self-change reaction. In which the delta G is equals to 0 and K equals to 1. Here is a perfect example of self-change reaction. And self-change reaction, in shorter words, is there's no change in bounding, and therefore there's no reaction going on. So delta G is equals to 0, and K will be equals to 1. But if we add the isotopic labels onto the reaction, we can see there is actually something going on, in which the isotopic labels plays an essentially important role in this reaction. So now we know the market theory is to justify the Alder-Spare mechanisms and investigate the relationship between the self-exchange reaction and e-transfer of the cross reaction. If we link back to the graph I've drawn a couple minutes ago, the factors may affect the rate of the Alder-Spare electron transfer, or I should say the overall activation may have 4 components. The first one would be delta G, double Jagger, W, and this would be the formation of the encounter complex. In which is close enough for electrons to fill in all the gaps to overcome the electrostatic repulsion. The second one is delta G double Jagger O, and this would simply just be the bound distance change. And the third component would be delta G double Jagger S, and this would simply be the summation sphere rearrangement. The fourth one would be simply just RT ln K HZ, and this is the usual collision frequency contribution, in which K would be ZE to the negative double G Jaeger over RT, and this would be the observed rate constant, which is equals to the collision frequency. And this would link to our Marquez equation, which is delta G double Jagger equals to lambda O plus delta G over 4 O to the square. And if we rearrange this equation, we get an equation like this, similar to Arrhenius equation, but it's quite different. And this relates the Gibbs activation energy to the standard reaction Gibbs energy and reorganization's energy, in which lambda includes the solvent reorganization and bond length change of reactants, in which lambda equals to lambda initiate plus lambda x. And based on this equation, we may get a graph like this. So the x-axis would be the reaction coordinate, and the y-axis would be the reaction Gibbs energy. Lambda is the distance from the bottom to here, that's lambda, and for lambda over 4 would be the distance between here and here, and the delta G double Jagger would be the bottom peak to the mark here. I would also like to point out the R here represents the potential energy surface of reactants plus environment, and the P here represents the potential energy surface of products plus environment. The thermodynamics driving force for the electron transfer may also affect the rate of the electron transfers. So we may draw the different conclusions with different delta G figures. So if delta G is greater to 0, it may lead to high activation barrier, in which the delta G Jagger will be increasing, so leads to the slow electron transfer. And if delta G is smaller than 0, it may lead to low activation barrier, in which delta G double Jaeger will be decreasing and leads to the fast electron transfer. And this would be condition 1 and condition 2. In condition 1, the graph may look like this. In which the delta G would be from here to here. Double G Jagger will be here to here, and normal delta G will be the bottom peak to the bottom here. In condition 2, it's just different, just symmetry different, and it will be looking like this. The delta G will still be the bottom to the bottom peak, and delta G double Jaeger will be similar to condition 1. This will be the end of my presentations. I hope you enjoy it, and do let me know if you have any more questions. Thank you, and I hope to see you soon.